Welcome everybody to the week 2 skills lab. I know it's going to be a little bit weird, a little bit different, not doing this in person, but we're doing the best we can with what we got. So this week we're going to have 3 questions. Going to be going over some acid-base stuff. And so let's get to it. So the first question says salicylic acid, which is that big long molecule, is a monoprotic acid. A saturated solution of salicylic acid contains 2.2 grams of the acid per liter of solution and has a pH of 2.43. What is the value of Ka? What is the value for Kb? So, let's go ahead and get started. So the first thing I'm going to do is I'm going to go ahead and write out the equation. So, C6H4OH COOH plus H2O goes to H3O plus aqueous, plus C6H4OH COO minus aqueous, and of course this is aqueous as well, and H2O is liquid. So we have 2.2 grams of the acid per liter of solution. So what we'd like to do is to get this to molarity. So start off with, let's go ahead and calculate the molar mass for our salicylic acid molecule. So altogether we have 7 carbons, 6 there and 1 there. And the molecular mass for that is 12 grams per mole. Plus, we have 1, 2, 3, 4, 5, 6 hydrogens. So 6 times 1. Put this in parentheses. And then we have 3 oxygens. So plus 3 times 16. And that should give us an answer of 138 grams per mole. Go ahead and double check that with my calculator. So now we have the molar mass. So let's go ahead and take our 2.2 grams and multiply it by 1 mole per 138 grams. And that should give us approximately 0.016 moles. So in order to convert this molarity, we're going to have to consider the solution, or the volume of solution. So it says 2.2 grams of acid per liter of solution. So it's really easy. We just have 0.016 moles per 1 liter of solution, which is going to equal 0.016 molarity. So now we have the molarity, the initial molarity of our acid. Now we can construct our ice table and get down to business. So I'm going to go ahead and write out this equation again. I'm going to pause it and get back to you guys when I do that. Okay, so I have this all written out. So let's go ahead and construct our ice table. So initially, as we just calculated, we have 0.016 molarity of our acid, and we have 0 for everything else. So our change is going to be minus x here. It's going to be plus x here and plus x here. So in equilibrium, I guess since equilibrium, we should probably have a back arrow as well. So in equilibrium, we're going to have 0.016 minus x. We're going to have x here. So we're not given a Ka. We're not given a value for it. But we are given a pH, and that equals 2.43. So you can kind of work backwards to figure out that Ka value. So let's go ahead and get to it. So our Ka, if we're just representing it with symbolically, it's going to be our H3O plus concentration multiplied by our C6H4OH COO minus concentration over our original acid concentration, which is C6H4OH COOH. So we need to find that X value in order to solve for this, because what this equals obviously is X times X over 0.016 minus X, like that. So how can we find that X? Well, what pH actually is, pH, as you remember, equals a negative log of our H3O plus concentration. So we can work backwards and figure out H3O plus concentration, which would give us that X value. So we have 2.43 equals the negative log of our H3O plus concentration. So let's go ahead and multiply each side by -1. We have -2.43 equals the log of our H3O plus concentration. And so our H3O plus concentration is going to be equal to 10 to the -2.43. And if we plug that in to our calculator, you'll find that that value right there, 10 to the -2.43, is equivalent to 3.72 times 10 to the -3, and that is equal to our X. So now it's pretty straightforward. Let's just go ahead and plug that in for everything, right? So we have X times X on top, so we have 3.72 times 10 to the -3 times, again, 3.72 times 10 to the -3 over 0.016 minus 3.72 times 10 to the -3. What that ends up being is 1.13 times 10 to the -3, and that is our Ka. We're not done quite yet. The second part of the question then, it says, what is the value for Kb? So if we recall, our Kw equals Ka times Kb. And so Kw is equal to 1.0 times 10 to the -14th, and that equals our Ka, which is 1.13 times 10 to the -3rd times our Kb. So our Kb, if we divide each side by that 1.13 times 10 to the -3, our Kb is going to be equal to 1.0 times 10 to the -14th over 1.13 times 10 to the -3. And that gives us a value of 8.85 times 10 to the -12. And so those are our answers for question number 1. So moving on to question 2. Question 2 says, calculate the pH of the solution obtained when 25.0 milliliters of 0.065 molar benzylamine, which is C7H7NH2, is titrated to the equivalence point with 0.050 molar hydrochloric acid. The Kb for benzylamine is 4.7 times 10 to the -10th. So right off the bat, I want to apologize for the shaky video. I'm kind of set up in my garage right now. It's about 4:45 in the morning. And I just kind of had to make a makeshift setup, some makeshift lighting, and this card table. So next week it should not be this shaky, so bear with me this week and get through it. So I'm titrating a weak base with a strong acid, and it's going to produce H2O and our ionic salt. So the first thing we want to do is we're going to want to find the moles that we have of our base. So it's pretty simple. We have 25 milliliters. And so let's go ahead and for the liters. So remember, 1 liter per every 1,000 milliliters. And that's going to give us 0.025 liters. So that's our volume of our base. So then we're going to take that, we're going to multiply it by the molarity. So liters times 0.065 moles per 1 liter. Now liters are going to cancel out, and that's going to leave us with approximately 1.63 times 10 to the negative 3 moles of our base. So that's how many moles of our base that we have in our solution. So if we take that number, 1.63 times 10 to the negative third moles, and I'm just going to say moles of base because I don't feel like writing that all out. Let's go ahead and figure out how much acid it's going to take to react with that. So it's our moles of base times 1 mole of acid, HCl, per 1 mole of base, because our ratio is 1 to 1. Our units can cancel out. And we find that's going to take the same amount of acid, or same number of moles of acid, to react with that. So what we're going to want to do now is we're going to want to find the volume. What volume of that acid is that going to take? So we were given a molarity of our acid. So let's go ahead and multiply the moles times that molarity, right? But we can't do moles over liters because we have moles on top here. So we're going to go ahead and put our liters on top. 1 liter per every 0.050 moles. And that's going to give us a volume of 0.0326 liters. So that's how many liters of our acid is going to take to titrate our base. So let's go ahead and find out the volume of our solution, the total volume. So the total volume of our solution with all of our acid and our base is going to be 0.025 liters from our base, plus the volume of our acid it took, which was 0.0326 liters, and we find it gives us a total volume of 0.0576 liters. Excellent. So that's the total volume of our solution after the titration has been carried out. And so now what we're going to want to find is we're going to want to find how many moles of our salt were produced in that reaction. Same deal as before. Let's go ahead and let's calculate it based off our base. So we have 1.63 times 10 to the negative third moles of base times 1 mole of our salt, which is this right here, per 1 mole of our base. Moles of base cancel out, and we are again left with 1.63 times 10 to the negative third moles, this time of salt. Cool. So now what we can do, we know the moles of salt, we know the total volume of solution, we can go ahead and find that molarity of that salt. It's as simple as taking our moles, 1.63 times 10 to the negative third moles, and dividing it by the liters of solution, which is 0.0576 liters. And that's going to give us a molarity of around 0.028 molarity. So, let's go ahead and take a look at this salt. Let's go ahead and try to predict whether it's going to be basic or an acidic salt. So, move this up, get it squared up. So, C7H7 and H3Cl. It's going to dissociate when put in water to C7H7 and H3 plus aqueous plus Cl minus aqueous. So, looking at these two compounds, these two ions, Cl minus is a conjugate base of a strong acid, so it's not going to react with water. But our C7H7 and H3 plus is the conjugate acid for a weak base, so that is going to react with water. So let's go ahead and take a look at that reaction. So C7H7 and H3 plus aqueous plus H2O. That is going to, so this is an acid, meaning it's going to go ahead and donate that proton, right? It's going to give out that proton. So that's going to give us H3O plus aqueous along with our base and H2 aqueous. So, very good. Let's go ahead and set the nice table. So, we know that initially we had 0.028 moles, molarity of that salt, right? And when it dissociates, this right here, this ion is going to be the same molarity as that of the salt, because it's just a 1-to-1 molar ratio. So let's go ahead and just start off with that. 0.028 molarity concentration for our positive ion, or in this case our acid, and then it's 0 for everything else, right? So our change for this is going to be minus x, this is going to be plus x, and this is going to be plus x. In our equilibrium, it's going to be 0.028 minus x. This is going to be x, and this is going to be x. So, if you go ahead and make an expression for our Ka, guys, sorry about that. Let's go ahead and adjust this. That looks fine. I'm going to go ahead and write this just a little bit lower. Our Ka is going to be our H3O concentration, H3O plus concentration, times our concentration of C7H7 and H2 over the concentration of that acid, our C7H7 and H3 plus. So, as it is, we actually don't know what that X is, and we also do not know what our Ka is. But if you recall, we were given a Kb. Write that over here. Kb was given as 4.7 times 10 to the negative 10th. And we can't use that as is, but what we do know is that Kw, which is a known value, it's a constant, is equal to Ka times Kb. Right? So if I want Ka, it's going to be equal to Kw divided by Kb. Sorry, that might be kind of small handwriting, but it means that our Ka is going to equal 1.0 times 10 to the negative 14th, And again, that's Kw. Kw is a constant. It never changes. Divided by Kb, which was given. That's 4.7 times 10 to the negative 10th. And that will give us a Ka of around 2.13 times 10 to the negative 5th. Good. Now we have our Ka. Let's go ahead and let's write out this, and let's sub in our symbols. Let me scoot that. So we have 2.13 times 10 to the negative 5th equals H3O concentration is going to be X, and so is our C7, H7, and H2. So it's going to be X times X, which is X squared on top, over, and then we have our acid concentration, which in equilibrium is 0.028 minus X. Well, this looks like a bit of a pain to solve, but we can employ a trick. So if you remember, if the initial concentration of our acid, which is 0.028, divided by the Ka, which is 2.13 times 10 to the negative 5th. If that is greater than 1,000, then we can disregard that minus X at the bottom. So when we do this, we find, yes, that is greater than 1,000. And so we can say that 0.028 minus X is approximately equal to 0.028. Remember that though, you can't always do that. I mean, sometimes you'll get unlucky, you'll have to use a quadratic equation. But this will save you a lot of time. Just remember that. The initial concentration of our acid divided by the Ka. Or if we're working with a base, the initial concentration of the base divided by the Kb. If that's greater than 1,000, then we can treat that minus X. Or if we have a plus X, we can treat that as negligible. So now we have 2.13 times 10 to the negative 5th equals X squared over 0.028. We're going to go ahead and multiply each side by 0.028. And we get 0.028 times our Ka, which is 2.13 times 10 to the negative 5th equals X squared. Square root both sides. And we get that X is equal to, I'm going to go ahead and plug this in my calculator. We find that X is equal to 7.72 times 10 to the negative 4th. That's good. We are almost done. We are very close. So we have one thing left to do. So our X, what does that represent? Well, that represents the concentration of our C7, H7, and H2. And also it represents the concentration of our H3O+. And we're looking for pH. And if you recall, pH is a negative log of the H3O+ concentration. Which is good. We have that. That's our X. So we plug X in, equals negative log of our 7.72 times 10 to the negative 4th. That gives us a pH of 3.11. And that right there is our answer. That is the pH of our solution. So problem number 3 is going to be a common ion effect problem. So problem number 3 says a solution is prepared to be 0.1 molar acetic acid, HC2, H3O2, and 0.20 molar sodium acetate, NaC2H3O2. What is the pH of this solution? Ka for acetic acid is 1.7 times 10 to the negative 5th. So I have this equation written out. This is dissociation of acetic acid. And I also am going to show that NaC2H3O2 is going to contribute to this concentration right here initially. So let's just jump right into it and make an ice table. So it says initially we have 0.1 molar acetic acid. And we have 0.20 molar sodium acetate added to the solution, meaning that our acetate concentration is going to be 0.20 molar. And quickly, the reason for this is obviously sodium acetate, Na(C2H3O2) associates in water to give Na plus. Oh, I guess that I should probably put that minus on there. Na plus C2H3O2 minus. Sorry, I forgot to put the minus on that acetate. So when we have 0.20 molar sodium acetate, we also get 0.20 molar acetate in solution. So initially, we start off with 0.1 molar, 0.2 molar, change to be minus X. We're going to have plus X plus X. Oh, and obviously our initial concentration of H3O is 0. And so our equilibrium for this is going to be 0.10 minus X. We're going to have X, and we're going to have 0.20 plus X. So let's go ahead and make an expression for our Ka. Ka is equal to our H3O plus concentration multiplied by our acetate concentration, C2H3O2 minus, over our original acid concentration, which is our C2H3O2. So let's go ahead and sub in our x's and all the other values. So this is going to look, after you sub that all in, like this. It's going to be X for H3O plus concentration times 0.20 plus X all over 0.10 minus X. And that's all equal to the Ka. And the Ka is actually given, so let's go ahead and write that in. 1.7 times 10 to the negative fifth. So that looks like quite the headache. That does not look like a fun thing to solve. But if you remember, we have a quick little trick that we can do. If we take the original concentration of our acid, which is 0.10, and divide it by the Ka, which is 1.7 times 10 to the negative fifth. If that's greater than 1,000, we got ourselves a little shortcut. We plug that into our calculators and we find that yes, that is greater than 1,000. So that means two things. One, that means that 0.20 plus X is approximately equal to 0.20. Also means that 0.10 minus X is approximately equal to 0.10. So it makes our life a lot easier. Let's go ahead, let's go in and let's write that in. So we have X times, instead of 0.20 plus X, it's just going to be 0.20. We're going to drop that plus X. Because it's so small, it's negligible. That's going to be over not 0.10 minus X, but just 0.10. And that equals 1.7 times 10 to the negative fifth. We're going to do some quick algebra. Multiply each side by 0.10. Multiply by 0.10. Those cancel out. So we get X times 0.20 is equal to 1.7 times 10 to the negative sixth. Divide each side by 0.20. We get that X is equal to 1.7 times 10 to the negative sixth over 0.20. So we plug that into our calculators. We find that that is approximately equal to 8.5 times 10 to the negative sixth. Yep. Let's go ahead and just double check that. Yep, that's correct. So now we have our x, and we're really close. So what is the question asking? It's asking for the pH. And now we have our x, and therefore, if I'm looking back up at the top, we have our H3O plus concentration. So our pH of the solution is going to be equal to the negative log for H3O plus concentration, which is going to be 8.5 times 10 to the negative 6th. Plug that into our calculator, we find that we have a pH of approximately 5.07. So that concludes this week's skills lab. I know it was only 3 questions, but I feel that any more would be almost too much. So I will be holding Zoom meetings or Zoom sessions in smaller groups. If you guys have questions, I hope that this was helpful, and feel free to message me if you guys have any questions. I'm in the class with you guys. I'm enrolled as a TA, so you guys can look me up and message me through Canvas. And yeah, so thank you for watching, and I hope this is helpful.